In these next lessons, we're going to consider formal definitions of limits. We have a general understanding of what limits are, and we know how to find them and use them in various contexts. But now we're going to go back and take a look at the formal, precise definition for limits. Calculus starts with a discussion of limits. All of the major ideas of calculus, continuity, differentiation, integration, series, are based on the limit concept. This study of infinity, whether infinitely large, infinitely small, infinitely far, or infinitely close, is the conceptual leap from algebra to calculus. The idea of a limit is the seed from which grows all of the rest of calculus theory. Informally, limits may be discussed numerically. For example, if we have the limit as x approaches -3 of 2x plus 5, maybe one of the first things you did when learning about limits was plug numbers into your calculator to get really close and see what happens. Looking at this chart here, as x approaches -3, what does it look like our function is approaching? It looks like in that box we would have a value of -1. We also consider limits graphically. Here we have our function f of x equals 2x plus 5. If we graph this, we would have a line with a y-intercept of 5 and a slope of 2. So when we approach -3 on the x-axis, we would be approaching -1 in the y direction. What about algebraic techniques? Of course, you may have already thought of this. If we want the limit as x approaches -3 of 2x plus 5, can't we just plug it in and get 2 times -3 plus 5, which is -6 plus 5, and that equals -1. So we already know that answer, right? Right, we do. But why are we allowed to do that? When can we just plug in to find the limit? Just plugging in assumes we have continuity of our function. How is continuity defined? Recall the definition of continuity. A function is continuous at a point C if the following 3 conditions are met. F of C is defined, the limit as x approaches C of f of x exists, and the limit as x approaches C of f of x equals f of C. Remember that when we talk about a function being continuous at a point, we can have the limit exist, so the limit has to exist as we approach C. But we also have to have the value of the function defined. But that's still not enough for continuity. The value of the function has to equal the limit of the function. The limit as x approaches C of f of x has to equal f of c in order for it to be continuous at the point. And of course, for a function to be continuous, it's continuous at every point. Think about this for a minute. Continuity is defined using limits. When we find a limit by just plugging in the value, we're using this third condition of the definition of continuity. We can use continuity to help us find a limit, but we can't use continuity to prove it actually is the limit, because when we're using continuity, we're using limits. So we cannot define limits using continuity because continuity is defined using limits. There's a circular argument and an issue here. We need a separate definition for limits that stands alone from continuity. These methods that we use to find and understand limits, numerically, graphically, algebraically, looking at limits, are good illustrations of the behavior of our function f of x. But they don't actually prove that as x gets arbitrarily close to -3, then f of x gets arbitrarily close to -1, the value that we found. How do we prove that -1 is actually the limit? What is the definition of a limit? The definition of a limit is as follows. Let f be a function defined on an open interval containing c, except possibly at c itself, and let L be a real number. The statement, the limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Whoa, what was all of that? You want to see a shorter definition? How about this? The limit as x approaches c of f of x equals L if and only if, for all epsilon greater than 0, there exists a delta greater than 0, such that the distance between f of x and L is less than epsilon for all x in the real numbers, such that the distance between x and c is less than delta. What? That's no better. That looks like just a bunch of crazy letters and symbols, huh? Well, let's break it down a little bit better. First, let's take a quick look at these symbols. Epsilon is the Greek letter E. We're going to think of this like error. Delta is the Greek letter D. So we're going to think of that like distance. Now, you're familiar with delta as a capital delta for change. This is our lowercase delta. We can think of this like a game. I claim that the limit as x approaches c of f of x equals L. That is my claim, my announcement to the world. Now you're going to challenge my claim. You challenge me by giving me an epsilon, an error, however tiny it is as long as it's positive. And my job is now to match that epsilon with a corresponding delta, a distance, so that for all x's within delta units of c, f of x will be within epsilon units of L. So take a look at some graphs. So here we have a function. As x approaches c, the limit is L. So that's my claim. Now you challenge me with some epsilon, some small distance around that limit. For example, you might say, you think the limit is L? Then can you get within 0.1 units of L? So now my job is to do a little calculation and find a value delta, a distance around C on the x-axis, so that any x within delta units of C will produce a y value that's within epsilon units of L. So if you tell me, for example, all right, get within 1/10 of the limit, I might calculate a delta distance of 1/2. So any value of x within 1/2 unit of C will produce a y value within 0.1 units of the limit. Well, maybe 0.1 is a big error. Maybe you want to challenge me further and say, get within 1/100th. Well, I can do a little calculation if that truly is the limit and find a new delta, a matching delta for your new challenge. What will need to happen with that delta? It will get smaller. It will get closer to C. So maybe my new delta is 1/5. So say any x within 1/5 of C will produce a y value within 1/100th of L. If I can find a matching delta for every possible epsilon, as long as epsilon is non-zero and stays positive, if I can find a matching delta, then that means the value L is the limit. Let's take a look at this definition again. The statement, the limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, there exists a delta greater than 0. So for every error in the y direction around L, there exists a delta, a distance in the x direction around C, such that if the absolute value of x minus c, that means the distance between x and c, is less than delta. So if x is within delta units of c, then the absolute value of f of x minus L, the distance between the corresponding y value and L, will be less than epsilon, less than the error given. Does this make a little bit more sense now? Let's see how this works through an example. Going back to the example we were looking at the beginning, the limit as x approaches -3 of 2x plus 5. Here what we want to do is find a delta greater than 0 such that the absolute value of f of x minus L is less than 1/100th whenever the absolute value of x minus c is less than delta. So let's identify the pieces. In this problem, what is our epsilon? Our error, our epsilon, is 1/100th. we see that up here in this expression where we have the absolute value of f of x minus L is less than 1/100th. What is c? What is x approaching? That's -3. How about f of x? Well, that's 2x plus 5. And the limit is -1. Now, it's important to note that the definition does not find the limit for us. Once we have the limit, we can work toward proving it is the limit. But the definition itself doesn't find the limit. We still need our graphical, numerical, and algebraic techniques in order to figure out what the limit is. To solve this problem, we're looking for delta that matches the epsilon of 1/100th. So when we set up these problems, we start with the information in the y direction. We start with, in this case, the absolute value of f of x minus L is less than epsilon, and we'll substitute in values. We'll substitute in our function 2x plus 5 minus -1, and that needs to be less than 1/100th. Our goal is to solve for what's happening in the x direction. The absolute value of x minus c is less than delta. In this case, that would be the absolute value of x minus -3 is less than delta, or x plus 3 is less than delta. So in order to find delta, we want to reorganize the inequality on the left to look like the inequality on the right. We want to take the inequality from the y information and make it look like the inequality from the x information. So simplifying this, we would have 2x plus 6 is less than, and I'm going to switch to decimal to make it a little simpler here, 0.01. So I can factor out a 2, and we have 2 times the absolute value of x plus 3 is less than 0.01. If we divide both sides by 2, we get the absolute value of x plus 3 is less than 0.005. So now this inequality matches the one we're looking for. So that means we can let delta equal 0.005. So for any x value that's closer than 0.005 to -3, the y value will be closer than 1/100th to -1. Maybe 1/100th isn't a good enough error for you. What if we pose a new challenge? How about epsilon equals 1/1000th, 0.001? Our setup is still the information in the y direction. The absolute value of f of x minus L is less than 0.001, our epsilon. The goal is to make it look like x minus c in absolute value is less than delta. Again, that would be x plus 3 is less than delta in this case. So if we substitute in 2x plus 5 minus -1 is less than 1/1000th, we get absolute value of 2x plus 6 is less than 0.001. We can factor out the 2, and we then will divide both sides by 2, and we get the absolute value of x plus 3 is less than 0.0005. Now we have a match. Our left inequality looks like the right inequality. Our setup was reorganized to meet our goal. So what we'll say is that we will let delta equal 0.0005. This would be the corresponding delta to an epsilon of 0.001. Maybe you're starting to see a pattern here. What if we have epsilon equal to 0.0006? Do you have a conjecture of what the answer would be? How about delta equals 0.0003? What did we do? We just divided by 2. Maybe you notice that's what we were doing in each of these examples up above. What we have done here is found specific deltas to go with specific epsilons that were given to us. But this doesn't prove that it works for all epsilon. We can't check every possible positive number epsilon. So how do we do the proof? For the proof, we will basically follow the same procedure as what we did above, but instead of using a number for epsilon, we'll just leave it as the variable epsilon. So our setup is the absolute value of f of x minus L is less than epsilon. Our goal is to reorganize it to look like absolute value of x minus c is less than delta. Again, what we'll have here is x minus -3 is less than delta, or absolute value of x plus 3 is less than delta. This is our goal, what we're trying to get it to look like. So when we substitute in the y information, we have absolute value of 2x plus 5 minus -1 in absolute value is less than epsilon. Epsilon in general. So simplifying, we have 2x plus 6 is less than epsilon. Factoring out the 2, we then have that multiplied times the absolute value of x plus 3 is less than epsilon. And when we divide by 2, we get the absolute value of x plus 3 is less than epsilon over 2. These now match, and we can say let delta equal epsilon over 2. Now we have a proof that for any epsilon, we can find a matching delta. In this case, if you challenge me with an epsilon, what I know to do is just divide it by 2 and I will find the matching delta. So no matter what epsilon you give me, there is a corresponding delta, so that if our x's are within delta units of c, the y values will be within epsilon units of L. Do you understand now how this proves it works for any epsilon, unlike when we plug in individual values? So this will be our proof. However, I need to make a little note here. Technically, this is not a formal proof. More formally, if we would say if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. If x is within delta units of c, then our f of x is within epsilon units of the limit. If absolute value of x minus c is less than delta, then we want to show that the inequality f of x minus L is less than epsilon follows. So substituting in, we would have x minus -3 is less than delta. Absolute value of x plus 3 is less than delta. And here we would say, let delta equal epsilon over 2. If we do that, then we get absolute value of x plus 3 is less than epsilon over 2. Multiplying both sides by 2, we have 2 times absolute value of x plus 3 is less than epsilon. And we can bring the 2 inside the absolute value there, and we can go ahead and split up that 6 to be 5 minus -1. And so now we've written absolute value of f of x minus L is less than epsilon. If this, then that. If we have the absolute value of x minus c is less than delta, then we can show the absolute value of f of x minus L is less than epsilon. Simple enough, right? But if you were reading this as a proof, what is the key step here? Here we have delta equals epsilon over 2. It looks like it's just pulled out of thin air. Where did that come from? Well, in order to do a proof like this, we have to do it the other way first. We have to actually calculate that relationship. So for our purposes, we're just going to stop once we have a relationship between delta and epsilon. Note that in your homework, the exercises are asking for proofs. So if you were to look in the solutions, there won't necessarily be an answer. A solution guide will look something like this because they're writing out the formal proof. I have posted the relationship answers for the deltas and the epsilons. So be sure to refer to that when checking your answers. Again, to reiterate, for our purposes, proofs will look like this. And our answers will be what we get when we have a relationship between delta and epsilon. This is the graph of 2x plus 5. But we're focused in here on the third quadrant, in particular near when x equals -3 and y equals -1. These green lines represent epsilon distances from the limit -1 in the y direction. The orange lines represent the corresponding distance delta. So as epsilon gets smaller and smaller, we're allowed less and less error. the corresponding deltas get smaller and smaller too. And since the limit exists, no matter how small epsilon is, the corresponding delta will always exist. It will get smaller as well, but we can always find a delta to correspond to a given epsilon. So in our example, we found one delta that matched a given epsilon. And that delta is a distance that would work in either direction around our value c. But that's not always the case. What if we have a curve like this? And let's say here we have some value c that we're approaching. So then our corresponding limit L here is on the y-axis. When we choose epsilon, epsilon is equally distant around the limit. So this value here and here should be the same in the y direction. But what happens to our corresponding value for delta? As we come down and consider what's going on the x-axis, do you notice anything here? We have two different widths. There's a delta 1 and a delta 2. The distance on the left does not necessarily match the distance on the right. So which one do we pick? Does it matter? Yes, it matters. We want to make sure that we pick the smaller delta. Now, in this case, that's the one on the right, but the smaller one could be the one on the left, depending on the shape of the curve. We need to pick the smaller delta because we need all x's within this domain to produce y values that are within the allowed error. So the smaller delta will work in both directions. Any x within this domain will give us y values within the allowed error. However, if we were to choose the larger delta, if we went the larger direction to both the right and the left, we would be okay here on the left side. But if we chose a value here on the right that's outside that delta window, our corresponding y value is now outside the allowed error. So when choosing delta, we want only one delta that goes with each epsilon. When choosing delta, we want to choose the smaller values. In fact, this is so important that if you're rounding off and say that you have a delta that equals 0.0449 and we want it to the hundredths place, we're not going to round up to 0.45 because that delta distance could be too wide. You would want to round it to 0.44 because then you know you're within the domain that will produce y values within the allowed error. Let's consider an example to see what this looks like algebraically. Here we're asked to prove that the limit as x approaches 6 of x squared minus 4x equals 12. And if you plug in 6, we'd get 36 minus 24, and that's 12. Keep in mind that the definition of a limit does not find the limit for us, but we'll use it to prove that what we think is the limit actually is the limit. So we'll set up the y information like we did before. The absolute value of f of x minus L is less than epsilon, and we want as our goal to make this inequality look like the absolute value of x minus 6 is less than delta. So substituting in our function, we have x squared minus 4x minus the limit 12. We can factor this trinomial to the quantity x plus 2 times the quantity x minus 6. We can write those as factors in absolute value. So we have the absolute value of x minus 6, which is what we're looking for in our goal. But we also have this absolute value of x plus 2. We cannot divide both sides by x plus 2 because we cannot have our delta depend on x. Delta can only depend on epsilon. So what we want to do is replace the absolute value of x plus 2 with a constant. So how do we figure out what that constant will be? Since we're only considering values of x near 6, we can assume that 5 is less than x is less than 7. That is, we can assume x is between 5 and 7. Because if the idea is that x is getting really close to 6, then we can assume that x is within 1 unit of 6. So we make an assumption distance of 1. We could make assumption distances of values other than 1, but it's a standard way to do it. If you change values, then the answers will change in the end. So it's best if we're all just consistent and use a standard assumption distance of 1. So if x is between 5 and 7, we can add 2 to all three parts of that inequality. So we end up with 7 is less than x plus 2 is less than 9, which means the absolute value of x plus 2 is less than 9. This is the maximum value of absolute value of x plus 2, so it will give us the smallest delta that we need. Now, wait a minute. Didn't I say earlier that we want the smaller value of delta? Why are we picking the 9 instead of the 7? Isn't 7 smaller? 7 is smaller than 9, but let's see how we're going to use that 9. When we substitute in the 9 for our constant, we now have 9 times the absolute value of x minus 6 is less than epsilon. So when we divide both sides by 9, we have the absolute value of x minus 6 is less than epsilon over 9. Epsilon over 9 is smaller than if we had used the 7, because then we would have had epsilon over 7. Epsilon over 7 would be the larger delta, and we need to choose the smaller delta. So by choosing the larger value in the inequality, we end up with the smaller delta. Now when we write our answer, we're going to write it a little differently than we had before. We will say, let delta equal the minimum of 1 and epsilon over 9. The 1 comes from our assumption distance, since we assumed we were at least as close as 1 unit to c, to 6 in this case. The epsilon over 9 is what we found for our formula. That's really the formula we would use if given an epsilon, we needed to find a matching delta. So we write our answers this way because it means that we had an assumption of 1 to get to that answer, epsilon over 9. The delta would be the smaller of those two values given an epsilon. One thing we can also do is check our answer by choosing some value of epsilon and then using our formula to find delta. We can calculate the y values when x equals c plus or minus delta. And then we make sure that those y values are within epsilon units of our limit. Say, for example, we had epsilon equals 0.01. If we calculate f of 6 plus 0.01 over 9, so that's 6 plus delta, where delta is epsilon over 9. If we calculated that, we would get 12.00889 and so forth. And if we calculated f of 6 minus delta, 6 minus 0.01 over 9, we would get 11.99111 and more. Now, what do you notice about these two values? They're very close to 12. That's because the y value is approaching 12 as the x values approach 6. However, it's not just that these values are close to 12, they're within 1/100th of 12. They are closer than 0.01 of 12. So that when we pick an x value within delta units of 6, we now have y values, f of x's, within epsilon units of our limit, 12. The blue curve here is x squared minus 4x. Notice that when x equals 6, y equals 12. The green lines represent the distance epsilon away from our limit 12. So we can squeeze these in closer and closer to 12 for different values for our error. But what about delta? Remember, in this example, we had two deltas. In our answer, we chose epsilon over 9. So all of the values for x that are within these orange bars, everything that's epsilon over 9 units away from 6, produces a y value within the allowed error. However, if we were to choose epsilon over 7, then there exists points where the x value is within the delta units within epsilon over 7, but then the y values are outside the allowed error. So we need to choose the smaller delta so that it works in both directions. It's certainly fine if there are places within the allowed error that are outside the distance, but what we're focusing on is all of the x's that are delta units away from 6 produces a y value within epsilon units of the limit. And then as epsilon is allowed to be smaller and smaller, those delta values will also get smaller and smaller as we approach our point 612. Here we have a new example. Prove the limit as x approaches 2 of 2x squared minus 3 equals 5 using the definition of a limit. Again, we will set up the problem as an inequality with the y information, and our goal will be to convert that into an inequality involving the x information. I'd like you to take a moment to pause the video and try this problem on your own. It'll be very similar to the one that we just completed in the notes. You will need to make an assumption along the way. I'll go through it with you here in a moment. Our setup for this problem in the y direction is the absolute value of f of x minus L is less than epsilon. Our goal is the absolute value of x minus c is less than delta. We want to make the left inequality look like the right inequality. This inequality on the right will become absolute value of x minus 2 is less than delta. So substituting in our function, we have 2x squared minus 3 minus the limit, which is 5 in absolute value, is less than epsilon. Simplifying, we get 2x squared minus 8 is less than epsilon. We can factor out a 2, and then we have x squared minus 4 is less than epsilon, which becomes 2 times the quantity x plus 2 times x minus 2 in absolute values for those is less than epsilon. So this is good news because we have the x minus 2 that we're looking for in our goal. But we also have this x plus 2 that we need to deal with. This is where we're going to make our assumption. Since x is approaching 2, we want to assume that x is between 1 and 3. So we're using that distance of 1 again. So now we want to replace x plus 2. So we need to add 2 to each part of the inequality. So that means we have 3 is less than x plus 2 is less than 5. So which of these do we want to use? The 3 or the 5? That's right, we want to use the 5 because it's the larger one here. So when we divide by 5, we'll get the smaller distance. So this becomes 2 times 5, since we're now replacing the x plus 2 with the value 5, times the absolute value of x minus 2 is less than epsilon. So we have 10 times x minus 2 is less than epsilon, or x minus 2 in absolute value is less than epsilon over 10. So our final answer will be to let delta equal the minimum of 1 and epsilon over 10. Again, the 1 comes from our assumption distance here, and the epsilon over 10 is what we calculate as our formula. Why are we going back and spending time on limits? Why is all of this so important? It is important that we develop limits exactly, since they are the foundation upon which everything else is built. For example, we already considered the definition of continuity. Continuity doesn't just depend on limits, it's defined by limits. In our definition of continuity, we not only have to have the function defined, but the limit has to exist and the limit has to equal the value of the function. Continuity is defined by limits. So if we don't have limits, we don't have continuity. And how many different theorems and ideas have we studied that start off with, if f is a continuous function, then... So very much limits are a foundation for the rest of calculus. Also, limits are crucial in the study of sequences and series. For example, the definition of the limit of a sequence. Listen to this. See if it sounds kind of familiar. Let L be a real number. The limit of a sequence an is L, written as the limit as n goes to infinity of an equals L, if for each epsilon greater than 0, there exists an m greater than 0. Such that the absolute value of an minus L is less than epsilon whenever n is greater than m. And of course, sequences that have limits converge, whereas sequences that do not have limits diverge. But let's take a look at that definition again. Look at these epsilons and greater thans and absolute values. This definition is similar to the definition we've just been studying. But now we're applying it to a sequence. In fact, this is the same kind of epsilon challenge as the limit of a function. If the limit as n goes to infinity of an equals L, then you can give me any small epsilon, and I can then find an m so that all of the an's with n greater than m are within epsilon units of the limit L. So let's take a look at the picture here. So we have a sequence, and I claim that the limit is L, that this sequence is approaching L as n goes to infinity. If that limit is the limit, then you can give me any small positive value for epsilon, an error, and I can find a value m such that for every n greater than m, all of the an's, all of the sequence values will be within the allowed error. If you give me a smaller epsilon, then that would just change my value of m and it would go down further. But everything past m is within the allowed error. Also, keep in mind that the sum of an infinite series is the limit of the sequence of partial sums. So if we have a series as n goes from 1 to infinity of an, that's the limit as n goes to infinity of the sequence of partial sums Sn, where each Sn is just the sum of the first n values. Don't worry about sequences and series right now, but we are going to talk more about limits with these horizontal asymptotes and other limits involving infinity in the next lesson. For now, our exercises will focus on functions that have a finite limit as we approach a finite value. You will have problems to solve where you're given a particular epsilon and you need to find the matching delta. There will also be exercises where you're asked to prove a limit, and we'll do that by just finding the formula for delta in terms of epsilon.